So 28 and 38. 21 and 38. Yeah.
All right, so the Zoom is up and we are recording so that we know. Rounds. Here we got. The 30-second. Yeah, I need to take this off the screen first because I need it.
Yeah. You are really gas. I mean.
All right, well, it is noontime. I'm gonna get started here. I hope you guys all got a restful weekend, because it's important to get enough rest. But at the same time, I also do not like the idea that the last time we met was on Wednesday. It still beats Friday only classes. You cannot believe how many Fridays we have holidays. And one of my colleagues teach a Friday only class, and she's having a really hard time catching up, just because there are so many Fridays that we are off, non-instructional Fridays. So, right. So are there any questions about the CNF homework assignment? I got, one, person coming into my office, to kind of check on the derivations, which is good. I mean, that's a good use of my office hour. Any other questions in general about that homework assignment? It is due on Wednesday. We're good over there. All right. Okay. Okay. So if there are no questions, there's not a whole lot I really can talk about in terms of the propositional logic thing, because until we actually get the next homework assignment, where we can talk about how to do the actual resolution, there's not a whole lot to talk about, because I can talk about it all I want, but it's not going to connect. It's not going to hook up in your mind. So there's not a whole lot to continue to talk. When we get the homework assignment due on Wednesday, that's when I can talk about okay, now that we know how to get this done, let's get that part done and so on. Okay. So for the time being, we're going to switch gear and move on to the next topic. So we're going to kind of go back and forth a little bit. There will be an overlap of topics because of the homework assignment is a little bit lagging behind. So the next big topic is counting. It is a part of discrete probability. So we'll go ahead and take a look at the concept of counting, which sounds really simple, right? Who doesn't know how to count? So counting is not specifically just counting, like 1, 2, 3, 4, 5. This is specifically about counting in the case of like how many unique lottery tickets can we get? All right. So can anyone imagine why this can be interesting to know? That sort of counting. It's also known as combinatorics. Okay, so if you want to know the branch of math that we are dealing with right now, is called combinatorics. So it is about counting the number of ways you can do certain things. Okay, and as a result, it also has to do with probability of what are the chances of blah blah blah. okay? So why do you think in computer science, it is important for us to derive, to know, to calculate the chances of X, Y, and Z? You can make predictions. Okay, very good. You can, yeah, go ahead.
Following on that idea of predictions, mass apply it, big data sets.
Okay, so you're talking about data science, which is a little bit different from combinatorics, okay? So if I give you a bag of marbles, okay, and each marble is numbered or they all have unique colors, okay? And I'm asking, if I want exactly this color, this color, and this color, and I ask you, what are the chances that, if you take 3 marbles out of the bag, it'll be that particular combination of colors? That's the kind of math that we are dealing with here. Okay, so the first interest, before I even go into the terms, the first thing we want to talk about is, the lottery tickets. Okay, in other words, what are the chances that if I go buy, the lottery ticket, what are the chances that I'm actually going to win the jackpot? So can you think of a reason why that might be useful? That might be meaningful? Yep.
Well, if you're the lottery runner, then
Mhm.
you have to determine how much each lottery ticket has to cost for you to make a profit based on how often people win.
Yep.
So you gotta know the total
Okay.
number and the rate that people win.
Mhm. And if you are one who is thinking about buying a lotto ticket, you might also want to know the chances of winning the lottery, how to call the highest prize, the jackpot, exactly. What are the chances of winning the jackpot in a lottery? Okay, so we'll kind of run with that for now. Okay, so let's just say that we are all thinking about buying a lotto ticket right after class today, and then the first thing we want to know is, well, is it worth it, right? What are the chances that I'm going to win the jackpot, or the chances that I would actually get more, I would get something back more than what I paid for, right? Because you don't have to win the jackpot to actually get something back. We'll go to the Lotto website and we'll learn the rules, and then we'll try to figure out the probability compared to how much you're paying. Then we can kind of calculate, okay, is it worth your money to buy a Lotto ticket? All right, so to all the people who are attending online, I do want to emphasize that everybody is only allowed your 3 allowances for participating online. So that means I will be tracking, who is participating online. And the 4th time, someone is participating online, it will be counted as an absent, because if this is a in-person class, it is not designed as an online class. So I just want to make that very clear. I hope everybody who's actually online is actually listening, because there's no way for me to tell. With you guys, I can tell, right? If somebody is dozing off and falling asleep, I can kind of tell, like, okay, maybe I should wake you up. But with people who are online, I have no idea, none whatsoever. But the rules will still be applied, just the same. All right, so let's go to the Lotto website, okay? Because I think that's going to be fun for us. So we'll look for Lotto and specifically the Powerball Lotto tickets. So we'll go to the website here and we'll take a look at the jackpot. So the jackpot is currently 122 million. So let's find out what it takes to win the jackpot, okay? Because most people are excited when they look at this number here. It's like $122 million. I can do a lot of stuff with $122 million. So we'll find out, whether it is a worthwhile thing to do. How much do you pay for each lotto ticket these days for Powerball? Is it $1 or $2? Does anyone know? $2? Yeah, that's what I thought. $2 to buy a ticket. All right. So the first thing we need to do, like everything else, is to learn the rules. Okay, so we are going to, let's see, no, not here. There's a link to actually learn about the rules. Let me see. Powerball, there we go. All right. So they have a lot of last draw details. So let's start with this and find out what these numbers are. So what these numbers are basically telling us is, they draw these numbers on a certain day. I cannot even remember what day. Is it Wednesday? Did they do it? I suppose we'll find out in how to play. But the last time they drew the numbers, no one won the jackpot. The jackpot is 5 plus Powerball, and you can see there's no ticket winning that number. Just matching the 5 numbers, not counting the Powerball, but there's also no winning ticket whatsoever. If there was one, it would worth 1.3, basically 1.36 million dollars. There's one single ticket winning, this particular prize here, which is 4 of the 5 lucky numbers plus the Powerball. There's only one ticket winning that, and it is $50,204. And then the rest are basically just looking at how many numbers out of the 5 you match, and then whether you also match the Powerball number or not. And then the number of tickets is over here, and then the number of the amount of money you win is over here. So do we have any questions about how to read this particular table? Okay, so we're good here. All right. So what we want to do is to go to how to play. So the instructions of how to play is actually quite interesting, especially the last step, but we'll get to that in a moment. Using a lottery play slip, otherwise known as a lottery ticket, which you can find at any lottery retailer, pick 5 numbers between 1 and 69 and 1 Powerball number between 1 and 26. Okay, so we'll just focus on this particular sentence here because there are some implications that is not clearly stated, okay? So when they say, pick 5 numbers between 1 and 69, can I pick like 1, 1, 1, 1, 1? Because there are 5 numbers and they are the same number, but that number is coming from between 1 and 69. So the answer is no, you cannot buy a ticket like that, okay? Because the 5 numbers, they all have to be different. So they did not say this, but it's actually pick 5 different numbers or unique numbers between 1 and 69. That's what it is, okay? And then you also have to pick a Powerball number or power number between 1 and 26. Once again, the rule is not very clear about whether that can overlap with one of the first 5 numbers that you have chosen. And the answer is yes, you can. In other words, the Powerball number or the power number is independent from the first 5 numbers that you choose. Is that okay? So the terminology is very important here. This is very imprecise, kind of language, okay? Because they did not use the word unique, because that would be useful in this case. Pick 5 unique numbers between 1 and 69, and 1 independent Powerball number, or the power number is independent to the 5 numbers that you chose earlier. So are we still doing okay so far with this? Okay, all right. You can also select your quick pick, which means you are not the one choosing. Some people use birth dates and stuff like that. They use exactly the same 5 numbers every single time because they think these are the 5 lucky numbers for me, okay? And if people do not believe in that, they can do the quick pick, which basically means that the system will pick those 5 numbers and plus the power number, or just ask the cashier for a Powerball quick pick, and the random number generator will choose the numbers for you. To play the same numbers for consecutive draws, just mark advanced play. So I guess that's for people who want to keep using the same 5 numbers. Okay, so do you think keep using the same 5 numbers would increase or decrease or not change the chances of winning? Not change. Okay, that is correct. Okay, so some people want to use exactly the same 5 numbers for basically personal subjective reasons. There's no objective reason whatsoever to keep using the same 5 numbers. Are we still doing okay so far? All right. Yep, go ahead.
2 tickets out of like you get more of a percentage. I think that would be like the only reason it exists.
But these are in consecutive draws. It's not in the same draw.
Oh.
Now, you can buy multiple tickets, you can say, I want to buy 1, 2, 3, 4, 5, 100 times. Here's $200. I want to buy 100 lotto tickets and they're all 1, 2, 3, 4, 5, and 6 as the power number. You can do that, okay? You can certainly do that. But in that case, it does not increase your chances of winning the jackpot, right? Or any of the other prizes. It just means that if you do win, then you get a better payoff, as a result, okay? Now, in the case of a jackpot, we'll deal with that later, okay? So for now, we're just gonna look at the basic, game rules. All right, you can play up to 10 consecutive draws on one pay slip by marking the advanced play box. So basically, you can pay, what, $20, I guess? So you can basically say, okay, from now, and for this and up to 9 draws after this particular draw, I'm going to use the same number. Yes. These are all ways to encourage people to spend more money, to buy lottery tickets, which is actually to you is a good thing because, education is one of the things that is partially funded by lottery, ticket, profits. So from your perspective as a student, this is a good thing. Step 2, pay $2 per play for each Powerball ticket. So that means, if you buy one that has, that you mark and have 10 consecutive draws, you'll be paying $20. Your ticket is your receipt. Once it prints, the play cannot be canceled or refunded. All right. Well, I guess, that's a no refund. So no one can say, I don't think it's a good idea. I want to, get a refund, give you back the ticket. Nope, you cannot do that. Step 3, know the draw times. Powerball draws take place on Mondays, Wednesdays, and Saturdays at right before 8 p.m. Draw entries closes at 7 p.m. on the day of the draw. I did not know that. I did not know that there are 3 draws per week. I thought that was only 1 per week, and there were actually 3. Remember that Powerball has 9 winning ball combinations. The more numbers on your ticket that match the number drawn, the more you win. I'm not really sure what that means. The Powerball has 9 winning ball combinations.
So like there's 9 sets of numbers, and then out of any of those sets, the more of that set that you get. So like if you get 4 plus the Powerball, then you obviously win a lot.
Go
But
ahead.
They all have to come from the
The
same.
list that we saw at the beginning, it's each of the 9 listings.
Oh, so that's what they meant. Okay, gotcha. Okay, so let me get back to. Okay, thank
Is
you.
there 9?
So there are 9 of these. Yep, there are 9 of these.
There you go.
Yep. But out of those 9, only 1, 2, 3, 4, 5, 6 involved, matching the Powerball. The rest are only matching the quote-unquote lucky numbers. Okay, cool. You can probably deduce that I do not play lotto at all. Have never once in my life, bought a single lotto ticket. Step 5, use any one of these ways to see if you are a Powerball winner, blah, 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 blah. And, oh, okay, they did not, I think they removed the one of the steps, which is, to dream on. Make plans for, spending the $122 million. Get a spreadsheet, get a wish list, All right, so they do publish the game odds, okay? So we'll get to the game odds in just a little bit because we want to independently derive the odds of winning, okay? All right, so given this, okay, there's one crucial information, or I should say, it is implicit, but it is important, okay? Does the ordering of the 5 numbers matter? In other words, is the ticket 1, 2, 3, 4, 5 the same as the ticket 5, 4, 3, 2, 1? The answer is yes. Ordering of the numbers does not matter. Okay, so that is important. They're only looking for membership within the 5 numbers that are drawn. They're not looking for which number drawn matches the number that you have chosen. So ordering is not important. Okay, so we have all of these important things, discussed at this point, not using the exact terminology that we'll be referring to later on, but I want to introduce the concepts first. Okay. Okay. So now the next question is, so how do we figure out, the chances of me winning the jackpot, which is $122 million this time? All right, so you can obviously ask Google. I'll bet you that Google can answer that question directly. You can also ask ChatGPT, which will probably explain to you, the actual odds of winning. But I'm not going to do either, okay? Because we want to figure out the actual rationale of doing all of this stuff here. And I don't doubt that ChatGPT may actually provide a reasonable or even better explanation than what I'm giving you guys. So that's going to be an interesting thing for higher ed is, are professors even going to be needed anymore when ChatGPT is good enough for teaching any concept that you ever want to learn? So that's an interesting question, especially from your perspective, because I'm close to retirement, so it's not going to be as big of a deal. But from your perspective, I think it's going to be interesting, okay? Because do you need to pay? I cannot even remember how much money per year to go to a UC these days. Does anyone know? I bet your parents know. Right? Okay, so let's just say we are going to UC Davis. Okay, is it close?
15K, and then another 15K for tuition.
So tuition itself is 15K already.
Something like
Wow. Okay, that's a lot more than when I went to college. I mean, I'm not just talking about inflation, because I think the cost of going to UCs and CSUs increases faster than inflation. So, all right. So, okay. So let's go ahead and do some calculations. And the way we're going to do the calculation is to use a spreadsheet, okay? Because the spreadsheets are really useful for this type of thing. So we'll go to do some calculations using our spreadsheet. So let me get to my Google Drive. And I'm going to put this into the shared folder. So if you guys want to access it, like even now during class, you can do so. So I'll put it into the shared folder and create. I mean, there are lots of stuff here already. I really need to organize my material. So we'll go ahead and create it and share. And I'm gonna name today's, name the spreadsheet after today's date, because this is a guarantee that it's not duplicate, or it has no collision with other things. So just to be sure, I will also add the name of the class. So this way we guarantee that there's no way that we can have a duplicate. All right, so what we want to do is to ask the question of, so how many tickets, how many unique tickets do we have? Okay, because if by answering that question, we'll indirectly answer the chances of winning the jackpot of Powerball. Okay, so if you think about a lotto ticket, how many ways can you choose the first number? So you have a completely blank sheet, okay, 5 spots. How many chances of how many ways can you choose the first number? It has to be a number between 1 to 69. Go ahead. 69, very good. Okay. And then for the second number, how many choices do you have? 68. And then the third number? Looks like there's a pattern here, right? 66 and then 65. All right, so if I multiply these 5 numbers, I will end up with the number of ways to choose the first 5 numbers, sort of, okay? There's a little bit problem here that I have not addressed yet, okay? But it seems like it's reasonable to multiply these 5 numbers and come up with a total number of choosing the first 5 numbers. And then you have the Powerball number. The Powerball number is between 1 and 29. So that means there are 29 ways to choose the Powerball number. All right. Does that make sense to me? Does that make sense to you? All
I
right,
think it was
yep.
26.
Oh, 26, okay, so let's make that 26. There we go. So that's for the Powerball. All right, so now we can do some calculations. So we can say, all right, so we'll go ahead and measure, to do the product. Is that a product function? No. There's a D product, M product, sum product. I'm just gonna multiply those numbers by hand. So we have A1 times A2 times A3 times A4 times A5 times A6. And, oh, okay, I did something.
B1, C1,
Oh,
B1.
right, okay. Thank you. Everything is transposed. There's actually a transpose function too, but we'll fix it in the correct way. So they're all in the same row, not the same column. D1, E1, F1. There we go. All right, so that's a gigantic, huge number, but I forgot to take one thing into consideration. Can someone remind me what I forgot to take into consideration? Well, yes, go ahead.
Powerball is independent for the fund.
No, this is gonna work, okay, in terms of the Powerball being independent from the other 5 numbers. All right, so one thing you can think about this is to think about this whole thing as a tree. Okay, yep, go ahead. That is correct, okay? Because in this way of measuring or counting the number of possible ways, I am assuming ordering is important. Okay, now, why is that the case? Because there are 69 ways to choose the first one, and then there's 68 to choose the second one, just right there. If I choose one first and then choose 2, that's considered a unique way of choosing compared to choosing 2 first and then choosing 1 second. So those 2 are considered different. Now, one way that I find is really useful for visualizing all of this stuff here is a graphical way. Okay, so I'm trying to determine whether to draw the picture using my tablet so it's recorded or to draw it on the whiteboard. Yes, go ahead.
But the ordering doesn't really change. No, it's still going to be 69 times 16.
Well, we'll find out, okay? Because once we see the picture, in the tree, we'll understand, why, this is actually double counting things, or it's not double counting, it's counting something 120 times, duplicating 120 times, exactly 120 times. Okay, so we'll get to that part, okay? But first, I have to, answer the question of, do I want to explain this on the whiteboard or do I want to record it? And I have no feedback whatsoever from people who are online because it matters the most to those people, right? Because you guys can all see the whiteboard. I'm getting no feedback from people who are online.
Tablet, if you can, please.
Thank you, very good. I'm just checking to make sure that you guys are still around. A few of these people I know they're around, but yeah. Okay, so I'm gonna use Zerno++, and then we'll do a mirror of that thing. So let me go back here. Yeah. All right, so the mirror is gonna be here. So this way you guys can see what I'm drawing. But I have to, kind of do it this way because the keyboard or the mouse or the pen can only work on my screen. And there's one more thing I need to do is to make sure the resolution is matching this. So give me one more second here. So I have to fix the coordinate system of the stylus. Okay, there we go. All right. So the thing is, you are starting here, okay? And you're trying to figure out what number to choose for the first slot on the ticket. So this is the first slot, okay, first slot. And we figured that there are 69 ways to do it, okay? And obviously, I'm not gonna spend my time to draw in number 1 all the way to 69. So we'll just say, okay, the first number can be 1, can be 2, can be 3, can be 4, blah, 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 all the way up to 69. That's how you choose, that's available for you to choose as the first number. So now I'm ready to choose my second number, okay? So for the second slot, if I chose 1 first, I can start with 2, I can choose 3, blah, 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 all the way up to 69. Okay, if I choose 2 first, I can choose 1 as my second. Does that make sense to you? Because I just cannot choose what I have chosen for the first slot, but anything else, between 1 and 69 is still available to me. So if I chose 2 first, then I have 1, then I have 3, all the way up to 69 as possible choices. If I chose 3 first, I can choose 1, I can choose 2, but I cannot choose 3 because 3 was already chosen in that scenario as my first choice for the first slot. So I will skip to 4 and then all the way up to 69. That's for 3 and so on. Does that make sense? Okay, do we have any questions here? But it is obvious from this particular screen, and I can use highlight here, that I am counting this as one way to choose, but I'm also counting this as another way to choose because they belong to 2 different branches in this particular tree. So if I were to expand this tree and finish it, okay, meaning that I have first, second, third, fourth, and fifth slot, then and at the end of drawing this tree, which is going to be gigantic, obviously I'm not going to do that. If I count the number of leaves in this particular tree, I'll be counting basically 69 times 68 times 67, 65, 66, and then 65. But I'll be counting a lot of duplicates. The question is, how many duplicates are we talking about? Because we can see right here, visually, we can see that 1, 2, and 2, 1 is already double counted because on a lotto ticket, ordering does not matter, right? But you can also kind of imagine in your head that 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, 2, 3, 4, 5, 1, 2, 5, 4, 3, 1, and so on. Those are all kind of duplicating. The question is, how many duplicates are we talking about? So let's go turn on to the next page. Okay. So we'll go to, let's see, go to journal, new page after. So we are now starting with a new page. So let's just say that we are focusing on 5 specific numbers that we have chosen. Okay. But instead of using numbers, which is going to be confusing, I'll just call those 5 numbers A, B, C, D, E. Is that okay? So each one of A, B, C, D, E is representing a unique number between 1 and 69, because my focus right now is to say, if based on those 5 numbers, how many ways can I arrange when ordering is important? Because that tells me the number of duplicates I have for every way to find 5 unique numbers. Does that make sense? All right. Okay. So now we're going to do it like this. Okay. So we have the first number, and then for the second number, it can be B, C, D, E. And then for the third number, if I have chosen A and B already, then the third number can only be C, D, or E. If I have chosen A, C already, the third number can only be B. A and C are used, so D and E over here. If I have chosen D already, then the third number can only be a B, a C, or E. And then for the last one, I can only have B, C, D left. Does that make sense? So you look at this and go like, oh, maybe I forgot one thing, didn't I? I forgot A. Yeah. Oh, the first one is, okay, never mind. Let's retract all of this. I should not have started off with A as a root node. The root node should not be anything. So my first one is A, B, C, D, or E. And then from A, I can choose B, C, D, E. From B, I can choose A, C, D, E. For C, I can choose A, B, D, E, and so on. Is that okay so far? You go like, but Tech, isn't this the same kind of picture that we had earlier? Except in this case, we only have 5 things to begin with instead of 69 things. You're correct. So if I were to continue this process, okay, so if I have chosen A, B already, then the next 3 I can choose would be C, D, E. If I had chosen C already, I only have D, E left. If I have chosen D already, the last one has to be E. Is that okay? So I'm not really exactly interested in exactly what letter goes where. I'm only interested in the branching factor of the branch out number. So with the first node or the first level of the tree, I got 5, right? The fan out is 5. The second level, the fan out is 4. And then for the third level, the fan out is 3, and then 2, and then 1. Is that okay? So if my interest is only on the number of leaf nodes in this particular tree, then what would that number be? The 120, because it is 5 times 4 times 3 times 2 times 1. So that means if I have 5 unique numbers, it will be counted 120 times in the previous page. Is that making sense? Are we good so far? I mean, it's these 2 slides look about the same thing. They are related, okay? Because the second slide, which is what we are looking at here, is telling us the number of duplicates that we will find in the previous one. So if I scroll back to the previous slide here, if I finish this really gigantic tree, because this one has 69 times 68 times 67 times 66 times 65 leaf nodes, out of those 120 of there'll be 120 of 1, 2, 3, 4, 5 in here, where 1, 2, 3, 4, 5 would be ordering in differently. If I have 2, 3, 4, 5, 6, there'll be 120 of those where the ordering is different, and so on. Does that make sense? Are we still doing okay? So that means if I'm only interested in the numbers of unique ways of choosing 5 numbers out of 69, what should I do? Okay, I'm going to switch back to the spreadsheet at this point, because the question is, there we go. So what should I do here? Not subtract, because out of this number, okay, the column G, row 1, out of G1, the number on G1, there are 120 of each that are duplicates. So what should I do? Division, okay, divided by 120. So I'm going to divide this by 120. Okay, so refer to this cell divided by 120. Then I get this number here. Okay, so take a look at this number. Approximately what are we talking about? We are looking at 292 million, approximately 300 million. Is that okay? So just kind of remember the order of magnitude, okay? 300 million. So now we switch back to the Powerball website, and then we go to the game odds page. And guess what? All 5 of 5 and Powerball is exactly that number. So it is a chance of 1 in 292 million, blah, blah, blah. Okay. So most of you, because you're in STEM, you're in a STEM subject area, you don't look at things in odds, you look at things in, okay, what is the probability, right? So let's figure out the probability. The probability is nothing more than just the reciprocal of the odds, right? So you divide, 292 million. You divide 1 by 292 million, which is a very tiny number. Okay, that's the probability. Okay, that's the probability of winning the jackpot. Are we good so far in terms of the math, in terms of how we got to the probability of winning the jackpot? You good? Okay. So here's a question. Why do you think that in the game odds here, they only specify the odds as 1 in so many, and instead of giving you the actual probability of point blah, 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 blah. Why is that? User friendly, very good. Okay, because a lot of people do not understand what does it mean with all of these zeros after the decimal point. This gives people, generally speaking, a better way to understand the odds. Once it gets beyond things that we can actually count or visualize, actually understanding the sense of order of magnitude is difficult for a lot of people, myself included. Okay, because once we get past hundreds and even thousands, it becomes more and more difficult to really get a sense of what that number is. Okay, how big a number is. All right, so are we good so far? So based on this, conclusion here, is it worthwhile to spend $2 to buy a lotto ticket? Nope. Okay, so at which point is it worthwhile to buy a lotto ticket? That becomes the next question, right? Okay, so let's try to figure that out. I think the math is going to be interesting. All right, so this is the number of unique tickets. And if you get a jackpot, you make $122 million, okay? So at which point of the jackpot is it worthwhile to buy a lotto ticket? So some people would look at this number and say, if I just multiply this number by 2, okay, 2 times, that would make it worthwhile to buy a lotto ticket, because the chances of my $2 to get a return is kind of worthwhile. Well, that is not the case. Okay, this is assuming, in other words, okay, let me try to rephrase this in another way. If you go to a bank, okay, I don't care which one, go to a bank, you take out a loan of this amount. So you go to a bank, you say, I want to borrow. Okay, how much do you want to borrow? What do you want to borrow it for? You want to buy a car or even a house? No, I want to borrow $584 million, $402,676. Okay, fine, you just have to sign here. So now you have money to buy all the possible tickets, right? Which means you're guaranteed to win the jackpot. Right? Does that make sense to you? Okay, does it make sense, with at least with regard to the part of if you buy every single possible ticket, you guarantee to win the jackpot. We good, right? Okay, and this is how much money you need to spend. And by the way, you also win all the other, kind of lesser, prizes, but they don't even add up to close to the order of $100 million. So we will just ignore those for now. Is that okay? But guess what? Uncle Sam comes along and say, you need to pay taxes for all this. So if your income, if you take this as a lump sum, Uncle Sam is going to go like, about 50% is going to state, local, and federal taxes. We'll just make an assumption about 50%, okay? Okay, well, let's factor that in, okay? So that means we'll say, let's multiply this by, since it's 50% that Uncle Sam wants, we need to multiply this by 2 so that we actually get to, this will break even, okay? This makes it possible for me to pay back the bank after tax. So I still have nothing in my pocket. But at least I get to conduct a very interesting experiment and be able to write about it and be able to produce a YouTube clip about it. And I may make more money from YouTube clicks, than, the lottery ticket itself, but it will still be an interesting experiment, right? But it's still not going to work out, okay? Because guess what? If this is a jackpot, which is 1 billion, basically $1.160 billion, you're not the only person who's saying, I'm going to buy the lotto ticket because there's enough money. So we are not factoring in the number of duplicate jackpot tickets. Now, that is not something that statistics or combinatorics can really help with because it depends on psychology. If everybody was to go through this class and understand, combinatorics and whatnot, you may have no one competing with you because nobody thinks it's worthwhile to do this. On the other hand, most people do not think like that, right? Most people look at this number, it's like 1.16B, I'm going for it, man. So you might end up with multiple, you're almost guaranteed to have multiple jackpot tickets. And the money is split amongst all the jackpot tickets. So now the question is, how many duplicate jackpot tickets are you anticipating? 2, 3, and so on? So that becomes an issue, right? So before I take roll today, I'm going to go with one more thing that I want to talk about, which is kind of interesting. It is not something that I have an answer for, but there are things you can do, okay? Because with all the AI and neural net learning and whatnot, because you can get past, you can go through all the past winning numbers. So we can look at all the past winning numbers, and we can go back and if they don't show the jackpot. Do you guys remember when the jackpot was really up in the 300 million something? I cannot either. It wasn't too long ago, so I'm just spot checking.
Probably find it somewhere.
Yeah. So anyway, you can actually model the number, okay? Because when the jackpot was really high, like this one, this is pretty high. February. Yeah, this is really high, okay, by comparison. So you can see that even when the jackpot was $747 million, no one won the jackpot. And you can basically, using this and using probability, you can go back and find out how many tickets were sold. Okay, or at least project, okay? It's not going to be a definite number, but you can actually go back and figure out how many tickets were sold. Why? Because we can plug in the equation, well, to go back to try to figure out how many tickets were sold, we just look at the probability of what are the chances that someone is just getting the Powerball number. That's easy because if you want to get the well, okay, I shouldn't say it's easy, but more or less it is easy, okay? Because you need all of the other numbers, the 5 numbers, not to match any of the winning numbers, and then you also need the Powerball number to match. So we'll talk about how to figure that part out too. But once we figure out the probability of just Powerball, then it's already published anyway, right? The odds are already published, so you can go backwards and figure out approximately how many tickets were sold.
Yeah, and then you can calculate the rate at which people are with the Powerball per ticket, and then you can determine how many duplicate tickets there's going to be.
You can also try to look into the past history like this. As the jackpot amount changes, how the number of tickets sold varies with the jackpot amount. Then you can have a projection of, okay, if the jackpot is up to 1.16 million, how many tickets would be sold, and then from that you can calculate the chances of duplicate tickets and so on. So you can turn this into more of a science, but since it does involve psychology, it's never really exact. Okay, are we still doing okay so far with all this? Okay, so I'm going to take a moment off here to take roll. So we'll go ahead and just make a duplicate of this. Okay, you won't be able to see it for a while. So I'll let you know when you can see it. All right, so we get here. We'll put this in discrete probability. And we'll put it at the top. We'll do the copy. And it's gonna take a little bit of time before it shows up, and then after it shows up, I suppose. Okay, do a refresh. All right, it shows up now. Oh. Wrong button. All right, so I'm gonna do some editing here. The QR code is not gonna work, okay, because I just changed the link. So I do want to change the date. Today is the 27th. And we'll change the passcode, get rid of the QR code. That's not gonna work. And we'll change the passcode, which is here. Obviously, change it to lotto. Or I can change it to the winning number of this round of the draw. Today is March. Oh, okay, just need to specify the time. Do you think 15 minutes will be sufficient? I think so. Okay, 1:05 p.m. 5:05 p.m. Save. There we go. So once again, the access code is Lotto. And the date of today is the 27th of March. Is the QR code method significantly faster or about the same? About the same. Okay. Oh. So out of the lecture up to this point, okay, the diagram, the tree, representation is actually important. It also tells us why we are multiplying 69, 68, and so on instead of adding the numbers. Because for each node of the first level, it has 68 children. For each of those children, it has 67 children. For each one of those nodes, it has 66 children, and so on. And that's why we are multiplying instead of adding. Yep.
Did you get 120 then?
The 120 is the same kind of thing, except the first level only has 5 nodes. And then the children of the first node, the first level nodes, each one has 4 children. And then after that, each one only has 3 children, and so on. I can show the picture.
Multiply all the.
Yeah, because the tree itself is uniform, which means at the same level, every node has the same number of children. And that's why just a straight multiplication of the fan out ratio is going to give us the answer. Yes.
Sorry, can you clarify? What was that, the third number? Because I saw you did 69, 68. I think I missed the Google sheet.
Oh, the Google Sheet. Okay. So it would be this one.
Yeah, for other context, what is that?
This is the Powerball number,
Okay. And
the
then-
number of Powerball numbers that we can choose from.
then G
Multiplication of A to F. And this is that number divided by 120 because there are 120 tickets that are actually duplicates of each other. Because in the game of Lotto, ordering does not matter. Are we still doing okay so far? All right, excellent. Okay, so now we want to kind of assign kind of formal names to things that we have just done, just so that we know what to call each thing. So we'll switch back to the diagram first. Okay, so when we switch back to the diagram, at each level, it is called a trial. Okay, so first slot is basically a trial. To choose the number for the second slot is another trial, and so on. So to choose the 5 numbers, we have 5 trials. So that entire thing, not including the selection of the Powerball number, is called an experiment. So an experiment is a sequence of trials. Each trial has a particular number of outcomes. And that's how we call these things. Now, so in this particular case, because anything that is chosen earlier cannot be used again, so it is also without replacement. Okay, so we have 69 things to choose from in the beginning. We have 5 trials. Each trial is without replacement. And we also want to take into consideration that ordering is not important, because there are cases where ordering is important. So are we okay so far with those terms? Okay. We good? All right. So the next thing we're going to do is to kind of take a look at what we call the birthday problem. Okay. The birthday problem is actually quite easy. It means, what are the chances that at least 2 people in a class like this share the same birth date? Okay, not including the year, but the same day of the year. That's the question. Okay, so just glancing at this class right now, I'm gonna guess we have approximately 25 people, physically here. Okay, we'll just call it 25. So with 25 people in the class, what are the chances that at least 2 people share the same birth date? That's the question. So now the question is, how do we figure that out? So any ideas? Go ahead.
Let's take into account biases, because we're most likely going to be this.
Yeah, we are not, yeah, we'll assume a uniform probability.
Yep.
Are we factoring
So just the day, not the date.
just the month and the day of month, but not the year? So the year is not taken into consideration.
Well, we still have to factor in leap years, because technically that's an extra day.
Yeah, we'll just we'll do the lazy thing and just say that, assume each year has 365 days. I don't even know what people do when they're born on a leap day. All right, so we'll just assume 365 days in a year. The question is, out of 25 people, what are the chances that at least 2 people share the same birth date? Okay, so you want to look at it in a reverse way. Okay, in other words, you want to ask the reverse question, which is, what are the chances that all 25 people in this class have unique birth dates? Okay, because once you answer that question, the other one is easy to answer. Are we doing okay so far? Okay. So I'm going to number people. So there's student number 1, student number 2, student number 3, all the way up to student number 27 in this class. The actual assignment is not important. It's just that you guys need to kind of imagine that you have a particular number associated with you. Is that okay? So now we're going to use the same approach here. Okay. I need to switch back to here. And we're going to use another page in this document. And I'm just trying to. Oh, there we go. We got a scroll bar. So we'll go ahead and make another page. All right, so in this case, we got student 1, and there are 25 students, right? But student 1 can choose from any one of the 365 days. Is that okay? Okay, so we'll say we got day 1 of the year, and then we got day 365 in the year. So once student 1 has declared, okay, this is my birth date, then student 2, okay, this is for student 2, how many days do you think student 2 can choose from in order for the class to have every person with a unique birth date? 364, very good. So if the first student has chosen the first day already, then the student can only choose from the second day of the entire year all the way up to the end of the year. If the first student has chosen the second day of the year, then if the first student has chosen the second day of the year, Then the second student can only choose the first day of the year, the third day of the year, all the way up to the last day of the year, and so on. Is that okay? So when you look at the fan out ratio, the fan out to the first student is 365. The fan out of the first student to the second student is 364, and so on. So it would seem like, oh, okay, we know how to do this, right? But the question is, how about the ordering? Is ordering actually important in this case? What do you think? So with this picture, we can already see, the example that I want to illustrate. So we want to look at this, okay? We want to look at this particular, what we call a permutation, because ordering is important, versus this particular permutation over here. Do you think they should be counted as two different ways of arranging things, or do you think they should be counted as one? They should be counted as two. Okay, because there's a chance that the first person is indeed born on January 1st. Okay, and then the second student is born on January 2nd. But that would not be the same as the number of ways in terms of, the first student born on the second day of the year versus the second student born on the first day of the year. Okay, so they will be counted separately. Okay, so as a result, in this case, there's no need to divide the whole thing by 1 times 2 times 3 all the way up to 25. Okay, so that means we just basically do a pi notation where I starts with 365 because that's a fan out of the first student. And then the last number is going to be 365 minus 24. Why not 25? Well, if you have 2 students, okay, then it would be from 365 to 364. That's why, okay, because it is 1 short. Okay, if you look at the difference here, it's going to be 1 short of the number of people because this is one person already. So we are looking at this, and the term we are multiplying is I itself. Is that okay? So let me ask one question first, because I was making an assumption which I thought was reasonable. It may not be. Does everybody understand the big pi notation? We should, right? Because I did spend, I cannot remember how much time to talk about the recursive definition of these big operators. So, all right. So the question is, and how do we calculate this? Well, fortunately, this is also known as permutation in the spreadsheet. So on the spreadsheet, you basically look at permut or permutation. We start with 365, and we have 25 trials in this case. Okay, without replacement, and ordering is important. So on the spreadsheet, that's all you need to punch in, okay, to figure out this number. It is pretty big, okay, so we'll go to a spreadsheet to kind of figure out that number. Oh, okay, I passed spreadsheet already. There we go. All right, so this is for the birthday problem. So basically, we just type in permut or for permutation, 365, 25 experiments, and this is the number. It's a pretty big number. So there are 4.92154 times 10 to the power of 63 ways to have each student, to have a unique birthday amongst 25 students. Is that okay so far? So you'll be looking at this number and go like, okay, so how is it helpful for me? Because this number is based on an assumption. It's based on the restriction already. It's based on the restriction that 25 people all have different birth dates in a year. Is that okay? But reality doesn't happen like that, right? Whether you are born on January 1st has no effect on whether you are born on the 1st of January. So that means, in reality, everybody can choose any day in a year as a birthday, right? So now the question is, So what number are we looking at then? If each person can choose any one day in a year as the birth date, okay, how many ways can we arrange that? So once again, to answer that question, it will be helpful to look at a tree, okay? This time the tree is similar to the previous one with a very minor difference. So once again, we have the first student, this is student one. Student one can choose any one of the 365 days. Okay, same as last time. It's student two. So for each way, student one choose a day in a year. Student two says, you know, I have the same number of choices because we don't have that restriction anymore. Because how birthdays distribute is unrelated to whether the first person has chosen a particular day in the year. So the second person also has 365 days to choose from. Same thing for the third student, also 365 days, and so on. So now we have 25 people, which means how do I calculate the number of leaf nodes in this case? Every level in this tree has exactly a fan out of 365. And there are 25 levels to this tree. So what is the number of leaf nodes in this case? It will be 365 for the first level, times 365 for the second level, times 365 for the third level. Yes. Yes, exactly. Okay, so if we want to look at the number of leaf nodes, it's going to be, if I still want to use the big pi notation, I can, but this time it is from 1 to 25 because we have that many students. But for each student, it is 365. We are just multiplying 365 25 times. Is that okay? So this pi notation is deceptive because all it really is trying to say is 365 to the power of 25. Are we good so far? All right. So now we look at this number and we punch this into the spreadsheet and figure out what number we are dealing with here. So we're going back to the spreadsheet. And we say, what is it power? It's power. 365 to the power of 25. That's also a pretty big number. That doesn't make sense. 365 to the power of 25. That's permutation. Oh, it does make sense. Okay, never mind. All right, so now we want to look at the probability. So let me describe these two numbers. A6 is the number of ways to have 25 people each having a unique birth date in a year. That's the total number, okay? And then B6 is telling us without any restriction, if anyone can choose any day in the year as a birth date, that's how many ways we can choose birthdays, including everybody has exactly the same birth date, which is January 1st. Everybody has the same birth date, which is January 2nd, and so on. So that's the total number of ways we can have birth dates naturally. So what do you think is going to be the probability of having 25 people all having unique birth dates in a class? It's a ratio. So what do you think, what we are dividing by what? Usually we should end up with a probability that is not greater than 1, right? So when you look at these two numbers, one is blah, blah, blah times 10 to the power 63. The other one is blah, blah, blah times 10 to the power 64. So which one do we divide by which other one? The smaller one divided by the bigger one. So we look at A6 divided by B6. That's the probability. So, but this is not what we are looking for. This is the opposite of what we are looking for. In other words, with a class of 25 people, there is a chance of 43.1 something percent that each person has a unique birthday. But my question was not that, right? My original question was, with 25 people, what are the chances that at least 2 people share the same birth date? Which is exactly opposite to what we just calculated. So what do I do to get to the number that I really want to get to? Subtract it from 1. Yep. So 1 minus this number here. I mean, you guys already kind of know it's more than half. So with only 25 people, the chances of 2 people having the same birth date in that class is more than 1/2. Did you expect that? It didn't seem natural, right? It didn't seem to make sense. It didn't seem intuitive at all. So you might want to ask the question is like, what if we have more people? So we'll go ahead and generalize the equation here, because what we need to parameterize would be the number of people. That number needs to be generalized. Okay, so let's go ahead and try to generalize that a little bit. I'm going to insert a column to the left. We'll start with 25, okay? But then every time I refer to 25 here, I refer to A6. Okay, I just click the N key unnecessarily. So A6 over here. And same thing over here. I refer to A6 instead of the constant. A6, there we go. This one is fine because it's referring to the other 2 cells, and this one is fine too because it's only referring to the previous cell. So this is one way you can kind of look into programming as well, because I'm just abstracting the original calculations and parameterize the one thing that I want to say, I want to keep changing this thing here, but everything else, the structure is right already. So I just need to look at the constant of 25 and say, replace all of those with a reference to the variable. So once I have done this, I can now go to the next row and say, well, let's think about 26 people. But instead of typing 26, I can now say, let's refer to this number and just add 1 to it. Then the rest, I can just copy, because this is how a spreadsheet is really, really helpful, is you can do something like this. So let's bump it up to the class size of my CISP440 in this semester. Okay, so we got 52 students-ish, in that class. So let's move on. I mean, you're looking at some insane numbers already, but we'll get all the way up to 52. So the chances of at least 2 people sharing the same birth date in a class of 52 is 97.8%. It's almost a sure thing. And you look at this and go like, but that doesn't make sense, because 52 compared to 365 is less than 1/7, right? I mean, we only got 1/7 of 365. How can this number be so close to 1 already when it is dealing with 52 students in the class? The math just works out this way. So do we have any questions about the birth date problem? Okay, so it's kind of interesting. Yep.
Is it like exponential? Like the closer you go to 365 students, the less it's going to go closer to 100.
Say that one more time.
So the more students you have, the less it will go to 100.
The more students, then the closer it gets to 100. Yes. Okay. Yep. So by the time we have 365 students, we will have 1.00. So it's not so much that we are getting closer, that this is monotonic, that it's going in the right direction. It is the pace it is going that is interesting. Because this one, it doesn't seem linear at all, right? Because we're only at 52 out of 365 days. So we still have a long way to go to say, okay, we got to have at least 1 student, or when we get to 366 students, then we guarantee that at least 2 people will share the same birth date. That's when we get to the 0.00 probability. But this is way below 366. How did we get that so fast, right? So it has to do with combinatorics, okay? So a lot of times what we think intuitively is like, well, maybe around 1/7 of the chance of people, all having, unique birthdays or whatnot. It doesn't work out that way. You got to work out the math, and then the math tells us a slightly different story. So do we have any questions about all of these calculations? So in reality, why do we care? If you're not going to buy a lotto ticket, I hope no one, well, okay, I shouldn't say that because in some way, I wish everybody is buying lotto tickets, so this way we get more money into education. But once we get education up, then it will also, inform people and say, well, you might want to buy a lotto ticket for just to be social, okay? Because all your colleagues are all buying, they're all pooling money and buying lotto tickets. You don't want to be the person who says, no, it does not make sense. You guys are all wrong. Okay, just out of that particular aspect, it's like, fine, here's my $2. So it's a self-limiting phenomenon, right? The more money we put into education, then we change the probability of people buying lotto tickets in the future. But why do we care in computer science about all of this stuff here? Are there any applications, where you encounter a situation where you have to go? Yeah, go ahead. It's a little bit different when it comes to decryption and encryption, like a hash function, that sort of stuff. But that's a very specialized area. Their numbers do matter. Because if you look at a hash function, does everybody understand what is a hash function, like MD5 or no? Okay, we'll look it up because it is an important topic, even though it's not directly related to combinatorics. Okay, so we want to look into hash function. So a hash function is any function that can be used to map data of arbitrary size, like your videos, your images and whatnot, to fixed size values, which typically would be 32 bits, 128 bits and so on and so forth. In other words, it's just a way to look at a arbitrary sized sequence of bytes and come up with a particular length of quote-unquote signature for that sequence of bytes. All right. So typically we are looking at 128, 256 bits in terms of the signature, but that can be coming out of one 1 gigabyte file. Okay. So that means there has to be collision. Does that make sense? Okay, because there are more possible files of 1 gigabyte than there are ways to arrange zeros and ones, even when you have 256 bits. Okay, yeah. So that's guaranteed. So the question is, what are the chances that can happen? With 256 bits, the chances is not that much. Okay, but when you look at MD5 hash, which has a checksum that is not nearly that long. So we look up MD5 as a hash function. The digest size is only 128 bits, which is still significant, but it's not really that much. So somebody actually compiled what we call a rainbow table. A rainbow table is used by hackers because sometimes people can hack into a database. They can find the hash value of passwords, but not the actual password itself. You cannot just enter the hash value in the field of the password and get into a system, because what you need to do is to enter a string of which the hash value matches what is in the database. Okay, so that means if you crack into a database, a system, you retrieve the entire database of all the hash value of the passwords, you still cannot get into the system. But with a rainbow table, which is reversing the whole process, given any hash value, here is a string that can generate this particular hash value. So with a rainbow table, if you can get to the hash value, you can get into the system. And because the rainbow table already exists for MD5, so MD5 is no longer considered a secure hash function anymore. Because if anyone can get to the hash value of a password, they can reverse the process and find a string that can give you exactly the same hash value. Now, is that string going to be the original password? maybe, maybe not, most likely not. It doesn't matter then, because it still gives you the same hash value. Is that okay? So the best, so I know this has nothing to do with, counting in the sense that we are talking about, but in case you guys are interested in encryption and stuff like that, the current standard of, hashing is using SHA to, hash value. And in that case, I think SHA-2 can have up to, the signature can be up to 512 bits. So in that case, okay, we do not currently have the computation nor storage capacity to do something like the same thing as a rainbow table. So it is still considered, secure when you use SHA, hash functions. So that's kind of, a little bit of, what hash values have to do with your passwords and hacking and so on and so forth. Just a little bit. All right, so we are getting to the end of this particular lecture. Yes.
This covers virus total checks for the files.
Yes. So this is why you get a checksum, of the files that you receive. So this way, if you get an update, okay, if Microsoft is pushing an update to your system, so at Microsoft.com, okay, they would publish the actual hash value. So when you download the file, there might be a chance that you're downloading from a source that is not Microsoft, but you want to check the hash value, because if the hash value is not the same, that means, you're definitely not getting the same file. Now, if you get the same hash value, it depends on which hash function they're using. If they're using MD5, they can still they can still manufacture a file so that the hash value is still matching, but it's not the same content. But I don't think people use MD5 hash even for that purpose anymore. So I think they're using, SHA-2, a longer signature. So this way it becomes impractical to try to find a way to defeat that system. Yep, so you're absolutely, that's what checksums are for. Yep. Yes, so MD5 is obsolete from the computer security perspective. So if you want to maintain a hash table from the perspective of data structure, it's still viable. I mean, there's no reason why you cannot use MD5 for that purpose, because it has no security implications. But for anything that has security implications, MD5 is useless. All right, I'll see you guys on Wednesday. So don't forget about the homework assignment, because I don't want someone to come to me on Wednesday and go like, but I did not know there's a homework. So if you got questions, I still have office hours before Wednesday. So you can go.
Started again. Yeah.